Good morning, students. I am going to discuss about theorem of three moment equation today. Let us have a brief introduction. As we know that beams are having more than one spark, generally it is called as continuous beams, and these beams are very common in bridge and building structures. Hence, one has to know how to analyze such kind of beams when they are subjected to transverse loads and support settlements, which are quite often in the design. When beam is continuous over more number of spans, supports, and are of different moment of inertia of spans. The force method of analysis is quite difficult if you consider the vertical support reactions as unknowns. However, this force method of analysis could be further simplified for these beams by choosing the unknown bending moments at the supports. Just we need to write one compatibility equation at each intermediate support of a continuous beam in terms of the loads on adjacent spans and bending moments at left, center, and right supports. So while writing this theorem of three moment equation, at a time we can consider only two consecutive spans. Since the compatibility equation is written in terms of three moments, therefore it is known as the equation of theorem of three moments. So while writing this equation, the most important point which we need to consider is each span shall be treated as a simply supported beam with external loads and two end support moments. For each intermediate support, one compatibility equation is written in terms of three moments. Thus, we get as many equations as there are unknowns. While writing the equation, you can see that at the maximum there are three unknowns, and this method was first introduced by Clapeyron in 1857. And you can find there are two theorem of three moment equation. One is simple theorem of three moment equation, generally which is applicable for without yielding of supports, and the other one called a modified theorem of three moment equation, or sometimes we can call it as a generalized theorem of three moment equation, which is applicable for yielding of supports also. Let us first look into the derivation of theorem of three moment equation without yielding of supports. Let us take a continuous beam which are subject to some random loading like this. Now, as we discussed earlier, each span shall be treated as a simply supported beam with given loading and end moments. So if I take the first span, let us consider this as a simply supported beam with this kind of given loading, and the fixed support can be replaced with an end moment here, and similarly the continuous support can be replaced with end moment. Like that, this span is considered as a simply supported beam with two end moments which are in positive direction. That is generally, as per our sign convention, the sagging moment is positive. And apart from that, there is an external load. Like that, each span shall be considered as simply supported span with two end moments and the applied loading. Now, this is the diagram you can find. Once if you consider each span as a simply supported beam, so using the principle of superposition, we can simply construct the bending moment diagram for each span. Let us take this particular span. Let us say this is left side support, this is the right side support, center support, and this is the right side support. We can represent, let us say the left side support is L, the center support is C, and the right side support is R. So therefore the corresponding moment, if you see that the moment at left side support we can designate it as ML. The center support is having two adjacent spans, therefore the moment can be represented as MC, and at the right support we can consider the moment as MR. Similarly, the span of the left side is, let us say, LL. The right side span is represented with LR. Let us assume the left side span is having the moment of inertia IL, and the right side span is having the moment of inertia IR. Now, at the continuous support, you can see that since it is having two adjacent spans, the rotation on the left hand side we can represent it as theta support at C, and on the left hand side, so we can write it as theta CL. And this rotation, this is on the right hand side for the support C. So therefore we can consider it as theta CR. Now if you see the bending moment diagram, if I am considering this as a simply supported beam due to given loading, whatever may be the loading, accordingly we can easily construct the bending moment diagram. Let us assume this is a random shape of bending moment diagram exclusively for this loading. And this is the moment diagram for the same span when it is subjected to two end moments. This is the moment Mn and this is the moment Mc. Therefore, this trapezium is the bend moment diagram for the applied moments. Similarly, if I consider this span, these are the end moments Mc and Mr. So this is the bend moment diagram for end supports, and this is the moment diagram due to given loading. It is a randomly drawn here, but as we know, depending upon the type of the loading, how the bending moment shape will be. So the same thing I explained here. Let ML, MC, MR are the support moments at left, center, and right respectively. The moments are taken to be positive when they cause tension at bottom. That is, as per our sign convention, the sagging moments are positive. Let IL, IR are the moment of inertia of left and right spans respectively. Let LL and LR are the left and right span lengths respectively. AL, AR are the area of bending moment diagram due to applied loading on left and right simply supported spans. Means after constructing this the bending moment diagram due to applied loading, we need to find the area of this diagram. Let us say this is the left side bending moment diagram. So the area of this one is AL, and this is the right side bending moment diagram. The area of bending moment diagram is ER. While applying this equation, as we said, this is without yielding or support, therefore it is assumed that the supports are unyielding. Now we need to relate the moments ML, MC, MR. Basically, these three are the unknowns as we have seen here, the support moments ML, MC, and MR. So we are considering two adjacent spans. So therefore, we are having three unknowns. Now we have to relate these three unknowns: moment at left support, moment at center, and moment at right support. So for this, let us use the moment area theorem. This relationship can be derived from the fact that the tangent to the elastic curve at C is horizontal. In other words, the joint C may be considered as rigid. If you see that the intermediate support here, if you draw the elastic curve here, it will be like this. And if I draw the tangent to the elastic curve exactly over the support C, it must be a straight line, it must be a horizontal. Means the summation of the rotations on the left and the right hand side supports, that is theta CL and theta CR, the algebraic summation must be equal to 0. So therefore, using that compatibility equation, we can write theta CL plus theta CR which is equal to 0. Now we have to find out what is theta CL, what is theta CR by using either moment area theorem or conjugate wave method or any other method. Let us try to apply the moment area theorem to find out these rotations, as we discussed in earlier semester, using the moment area theorem how to find out the rotation. Let us take a simple supported beam like this, and this is the elastic curve and this is the rotation theta CL. If I want to find out the rotation theta CL using the moment area theorem, what we need to is we need to draw a tangent at center support, then take the vertical intercept. So this vertical intercept is nothing but the moment of area of M by A diagram of this particular span about this left support. And once if you know the vertical intercept, that divided by the span gives the rotation. So therefore, the theta CL is nothing but the deflection of L from tangent drawn at C divided by the span. The deflection of L from tangent drawn at C is simply nothing but the moment of M by A diagram between C and L about L divided by span, that is IL. Now let us try to write that equation now. The moment of M by A diagram, what is the moment of the area of Empire diagram? That is, let us assume that the area of this diagram is A M by I. Means this area is AL divided by IL. This is nothing but M by I multiplied by its central distance from the left support, that is XL bar. So this gives the moment of area of M by I diagram about left support, plus two end moments are there here. One is ML, the other one is MC. So the moment of area of M by I diagram due to support moments. You can make into two triangles like this. This is one triangle and this is another triangle. Now the area of this triangle is half into height into base divided by A, that is half into ML by AL into LL gives the area, multiplied by the central distance 1/3 L, that is 1/3 of left span. Similarly, the moment of area of this triangle half into MC by AL into LL, and its central distance from here is 2/3 L. So therefore, the first part is the moment of area of Empire diagram of left support. This is the moment of area of Empire diagram of support moment. And again, this is the moment of area of Empire diagram about L of this particular support moment. So now if you simplify this equation, we will get theta CL equal to AL XL bar by AL LL plus ML LL by 6CIL plus MC LL by 3IL. Let us see equation 1.2. So this AL and AR generally in the next equation are the area of the bend moment diagram due to applied loads on left and right spans. XL and XR denote their respective central distances from the left support and right support respectively. And this is the central distance of this left side free diagram on the left support. XR is the central distance from the right support of the right side simply supported bend moment diagram. Similarly, if you write for theta CR, like theta CL, if you write for theta CR, so you will get the equation theta CR equal to AR XR bar by AR plus MR LR by 6CIR plus MC LR by 3IR. Now apply these two in the compatibility equation. If you substitute it, that is theta CL plus theta CR equal to 0. So this is theta CL and this is theta CR, and if you equate it to 0, and if you rewrite this equation, you will get a nice equation, that is ML into LL by IL plus 2 times MC into LL by IL plus LR by IR plus MR into LR by IR, that is equal to minus 6AR XR bar by IR LR minus 6AL XL bar by IL EL. So this equation we will be calling as simple equation for theorem of three moments. So now you need to remember this equation while solving the problems. It is very simple. ML is the left side moment, left hand side support moment, multiplied by LL by L, that is the ratio of span to its moment of inertia. Then 2 times center support moment, multiplied by summation of ratio of left side span to moment of inertia and right side span to moment of inertia, plus moment at right hand side support multiplied by the ratio of span to its moment of inertia equal to minus 6AR XR bar by IR LR minus 6AL XL bar by IL LL. So ML is the left hand side moment, MC is the center moment, and MR is the moment at the right hand side support. AR is the area of the bend moment diagram on the right hand side span due to applied loading. XR is its corresponding central distance from the right hand side support. AL is the area of the left hand side bend moment diagram due to applied loading. XL is the corresponding central distance from the left hand side support. So this equation we are calling it as three moment equation. It relates three support moments as you can see here. One moment at left hand support, one moment at at center support, one moment at right hand side support. So this relates three support moments with the applied loading on two adjacent spans. The important note here is if there are more than one type of loading on a single span, let us take a uniform distributed load, some concentrated load, some couple is there. Then the most easiest way to consider such kind of diagrams are, let us work out individually, means it is using superposition. First you take the Benamou diagram due to concentrated load, then you take the Benamou diagram due to UDL, then you take the Benamou diagram due to couple and superpose them. Now let us take an example. Here a continuous beam ABCD is carrying a uniformly distributed load of 1 kN per meter over span in addition to concentrated loads as shown in figure. Calculate the support reactions, also draw the bend moment and shear force diagrams. Assume ABC, EI to be constant for all members. This is a simple beam. ABC is a continuous beam, ABCD is a continuous beam, CD is a overhang portion. It is subjected to a uniformly distributed load of 1 kN per meter and there is a concentrated load of 1 kN and here there is a concentrated load of 5 kN. The spans are mentioned like this. Now the first step what we have to do is, first we have to consider each span as a simply supported beam. Means we have to treat AB is a one simply supported beam, BC is a one simply supported beam with end moments. Here if I take AB as a simply supported beam, let us say assume the moment here is MA in clockwise direction, here the moment MB in anti-clockwise. Similarly, while treating this BC, the same moment is applied in opposite direction here and here it is MC. Now here since it is a overhang portion, we can consider the effect of this overhang portion into a support moment here. What will be the moment due to this overhang portion? It is simply nothing but this load multiplied by this distance, 5 into 3, 15 kN. How it is acting? Since the load is acting in downward direction, so if I take the moment here, it is acting in this particular direction. Means it is a hogging in nature. It is a minus 15 kN here. Now let us see. So this is a continuous beam. Now if I take AB as a simply supported beam, it is subjected to one concentrated load and a uniformly distributed load. Now let us try to bend moment diagram for this simply supported beam. How do you draw this? First we take the uniformly distributed load. The bend moment diagram due to uniformly distributed load is a parabola with maximum moment at center is WL square by 8. That is 1 into 10 square by 8. That is 1.5 kN. And another load is also there. That is a concentrated load. As I said, you have to consider the easiest way to consider is considered separately. Now let us try to draw the bend moment diagram for concentrated load. When a simply supported beam subjected to concentrated load, the bend moment diagram is a triangle and the maximum moment under the load is or at center is WL by 4, that is 1 into 10 by 4, that is 2.5 kN. And similarly the bend moment diagram for this simply supported beam, it is subjected to UDL, therefore the bend moment diagram is a parabola and maximum moment at center is WL square by 8, that is 12.5. Now after this is the first step. First we have to consider each beam as a simply supported beam and draw the bend moment diagram due to the given loading. So this is the bend moment diagram due to UDL, this is the bend moment diagram due to concentrated load and this is the bend moment diagram due to UDL for the right side span. And after that we have to find out the area of each bend moment diagram, because in the expression we need AL and AR. So you calculate what is the area of this bend moment diagram, that is 2/3 BH, and similarly what is the area of this bend moment diagram, that is 2/3 BH, means 2/3 into 10 into 12.5, this gives 83.3. Similarly the area of this, and similarly the area of this triangle, that is half BH, half into 10 into 2.5, that is 12.5 is the area. And for the left side bend moment diagram, we have to find out the CG from the left hand side support, and for the right side pendulum move diagram, we have to find out the CG from the right hand side support. Since it is symmetrically loaded, the centroid is lies at center, therefore that is at 5 meters. Again, this is central concentrated load. The CG exactly at the center, that is at 5 meters. And apart from this, what we have to consider? We have to consider the end moments. Here it is MB, here it is MB. We will consider later. So now, by inspection, it is assumed that the support moment at A is 0 because it is a simply supported end. Therefore, the moment at A is 0. And here, the moment at C is not 0 because of the overhang portion. It is subjected to some moment, that is nothing but 5 into 3. It is 15 kilonewton meters. That is acting in this direction, means it is in hogging in nature. Therefore, the sign is negative sign. That is what I have written here. By inspection, it is assumed that the support moment at A is 0 because of the simply supported end, and the support moment at C is 15 kilonewton meters minus because of the hogging in nature. Now, only you can find the redundant in this equation, in this problem is the moment at A is 0, the moment at C is known, so the unknown moment is only one, that is at B. So hence only one redundant moment MB, which is to be evaluated. So how many equations we require? Since only one unknown is there, so therefore we need only one equation. So while applying this theorem of three moment equation, as I said, that can be applied only to adjacent spans once. Means here two adjacent spans means AB and BC first. So only one unknown is there, therefore only two adjacent spans are here. Now if you write the theorem of three moment equation for this is our theorem of three moment equation. ML into IL by LL, LL by L plus 2MC into LL by L plus LR by R plus MR into LR by R, which is equal to minus 6AR XR bar by IR LR minus 6AL XL bar by IL LL. Now if you apply this equation for this problem, 2 times MC multiplied by, since A is constant, so both sides gets cancelled, I gets cancelled. Now LL, that is the left side span, 10 meters, plus LR, right side span, 10 meters, plus MR, that is moment at right hand side support here, multiplied by LR, that is the right hand side span, 10 meters, which is equal to minus 6AR XR bar by LR minus 6AL XL bar by IL. Now if you substitute the values from the bending moment diagrams, that is 10 plus 10 20 into 2 40 MB. This is MC is known. MC is minus 15 into 10 minus 150, which is equal to minus 6 into ER. As we calculated here, area of this diagram is 83.3 into XR bar 5 meters, 6 into 83.3 into 5 by span 10 minus due to triangular loading. The area is 12.5 and its central distance is 5 minus 6 into 12.5. It's a mistake. 12.5 into 5 by 10 minus the right side area of bending moment diagram 6 into ER 83.3 into its corresponding central distance from the right side support. Please remember while writing this, when you are taking the left side fibra diagram, bending moment diagram, you have to consider the central distance from the left hand side support. When you are writing the right side bending moment diagram area, we have to write the central distance from the right hand side support. This is very important, you have to remember. So 83.33 into 5 by 10. So now if you simplify this, MB equal to minus 18.125 kilonewton meters. So once if you know the moment, now you can find out the support reactions by using simple equilibrium equations. Just take the moments of the forces about point B. If you take it, RA into 10 minus 10 into 5 minus 10 into 5 plus 18.125 equal to 0. So from this you get the reactive forces for span AB. So while applying these equilibrium equations, again you need not apply the whole beam. Just simply you consider one beam. Now this moment is known in this direction. So now consider only this simply supported beam and calculate the reaction at A. And while calculating the reaction at B, we have the reaction on the left hand side, reaction on the right hand side. When you are taking AB, we will get this side reaction, that is RBL. And while taking BC, we will get RBC, RBR. What is total reaction? The total reaction is simply nothing but summation of the left hand side shear and the right hand side shear. That means RBL and RBR. So let us see. That is what I have written here. If you consider span AB, if you write the moment equilibrium equation, you will get RA and RBL. Similarly, while applying for span BC simple moment equilibrium equation, you will get RC and RBL. Or else, here you can see that directly you can calculate also. This is what I am telling. Let's take first simple supported beam AB. This is the given loading 1 kilonewton, not 10 kilonewton. This is 1 kilonewton. This is 1 kilonewton per meter. We have got the end moment 17.875 kilonewton meters minus, means earlier we assumed in clockwise, but now sagging, but at the end we got the minus sign, it is acting in opposite direction, that is hogging. Now how do you find out the support reaction? Simple. You see this. First you find out the support reaction to UDL. It is simply supported beam subjected to UDL. The reaction is WL by 2. This one 1 into 10 by 2, that is 5 kilonewtons. This reaction is 1 into 10 by 2, 5 kilonewtons. Since the load is downwards, the reactions are upwards. Then you take the concentrated load, that is 10 kilonewton. Therefore, the reaction is W by 2, 10 by 2, 5 kilonewton, and 10 by 2, 5 kilonewton. Now, UDL is over, concentrated is over. Let us come to the moments. Here there is no moment. Here there is no moment. Now, what is happening now? The resultant moment is acting in this direction. Therefore, to balance this resultant moment, the coupled cusp must be created by support reactions. What should be the coupled direction? When the resultant moment is acting like this, the coupled to reactive forces must be in opposite direction. Means this reaction must be upwards and this reaction must be downwards. What will be the magnitude of this reaction? The algebraic sum of these two moments are the difference in moments divided by span. Here it is 0, here it is 17.875. So 17.875 plus 0 divided by span, that is 10 meters. It is 1.787. This is 1.787, but this is upwards and this is downwards. Now the resultant reaction, if you see that summation of these three, this and this are upwards, this is downwards, therefore the resultant is upwards. Here it is all the three are upwards, therefore the resultant is upwards. This is the left side reaction for support B. Now coming to the span BC, we have the moment at P here and there is a moment at C here 15 kilonewtons. So therefore, if you work out due to UDL, WL by 2, WL by 2, due to unbalanced moments, here it is 17.875 is acting in anti-clockwise direction, here 15 is acting in clockwise direction. Therefore, the resultant moment is 17.875 minus 15, which is in anti-clockwise direction. Therefore, the couple must be in clockwise direction. Means this reaction must be upwards and this reaction must be downwards. Therefore, what is the reactive value? The difference of these two moments, 17.875 minus 15 divided by span, that is 0.2875. This is 0.2875. Therefore, the resultant reaction is 5 plus 0.2875, and here the resultant reaction is on the right hand side, left hand side, 5 minus 0.2875. And if I consider the overhand portion, there is a concentrated load here. Therefore, the shear on the right hand side span is 5 kilonewtons. Now, let us see how to draw the shear force diagram. Now, once if you know the shear forces now, First there is a reaction. Since it is a UDL, the variation is linear. Then there is a concentrated load. Again UDL is there, it is a linear variation. Then this is the left hand side support reaction support B. This is the right hand side support reaction support B upwards. It is subjected to UDL again, so therefore the variation is linear. Then there is a left hand side support reaction at C, and then there is a right hand side support reaction at C. Since there is no load here, it is constant, then there is a concentrated load 5 kN. And while drawing the Benamou diagram also, the best way is to consider each span as a simply supported beam. First we draw the Benamou diagram due to loading, and over that you superpose the Benamou diagram due to end moments. Let us see. So this is the Benamou diagram due to concentrated load and UDL, and for this span again this is the Benamou diagram due to UDL, and this is the that's all. Now the moment diagram due to end moments, here it is 0 moment, here it is 17.875 kN, therefore it is a triangle. Now again here it is 15 kN, here it is 17.875, so therefore it is a trapezium. Now here it is a concentrated load, here it is a 15 kN, it's a triangle. Now just the moment diagram due to loading is positive and the moment diagram due to end moment is negative. Now if you superpose this, the resultant moment diagram will be this hatched portion. This portion gets cancelled, this common portion gets cancelled. The uncommon portion is the resultant Benamou diagram. We have to simply hatch it like this area. You can see this one here. This is the resultant Benamou diagram you can find. Let's take another example quickly. A continuous beam ABC is carrying uniformly distributed load of 2 kN per meter as shown in figure. The moment of inertia of span AB is twice that of span BC. Evaluate the reactions and draw the Benamou and shear force diagrams. Now, this is another typical problem now. So here the support is fixed support and it is a 2-span continuous beam subjected to a uniformly distributed load. The moment of inertia of this span is 2I and the moment of this span is I. This is 10 meter span and this is 5 meter span. Now if you see that the unknowns in this particular case are simply nothing but your static indeterminacy. Here one moment and here one moment, and here the moment is 0 because of simply supported end. So how many unknown moments are there? One at support A, one at support B. So therefore there are 2 unknown moments. Means how many theorem of 3 moments we require to write? 2, because 2 unknowns means 2 simultaneous equations are required. So by inspection the moment at C is 0, as we said it is a simply supported end. Therefore the moment at A and moment at B need to be evaluated. Now if you write the theorem of the moment equation, or in the other way you can also write the compatibility equation at B is what? The rotation to the left of the support B and the rotation to the right of support B is 0. Means the tangent becomes horizontal here. So theta BL and theta BR, summation of those two must be equal to 0. So you can find out the compatibility condition corresponding to related moment at A is theta A is 0. What is the compatibility equation at A? This is the compatibility equation at support B. And what is the compatibility equation at support A? Since it is a fixed support, the tangent to the elastic curve is horizontal here. Therefore, the rotation at A is 0. Means the compatibility equation at support A is 0. So now you can find out the end moment, or you can write the compatibility equation without considering the theorem of 3 moment equation also. That is how to write it. You see this. Now if I take the first span AB, it is subjected to UDL. There is an end moment MB to the left side and end moment MA. The Benamou diagram due to loading is parabola. Let us say its area is AL and its central distance is x bar. And the Benamou diagram due to end moments, this is clockwise, this is clockwise. So if if I take separately 0 moment with MB, MA, this is a triangle. Here it is 0 moment, MB, it is a triangle. Or you can consider as a trapezium. MA, MB, and you join by a straight line. You will get a trapezium. Now the slope at A, theta A, may be calculated from moment area theorem. Theta A is simply nothing but area of M by A diagram between A and B. Isn't it? So now if you write it, the area of this diagram, the area of this diagram, the area of this diagram, that gives theta A equal to area of all the three diagrams. And what is the compatibility equation? The slope at A is 0, theta A equal to 0. This is one way of calculating the moment at B or the equation. But now if you apply theorem of three moment equation instead of this one, what is the procedure? Here, whenever there is a fixed support, we need to make a slight modification in that while applying this theorem of three moment equation. See, what we have to do is, here how many unknowns we have? Moment at A is an unknown, moment at B is an unknown. And theorem of three moment equation can be applied for two adjacent spans. Now here we have two spans. So how many equations I can write? To be frank, I can write only one equation. But how many unknowns are there? Moment at B and moment at A are the unknowns. So therefore, we need to make a slight modification whenever this kind of fixed support is there. What is that modification? Here you see. We have to assume an imaginary span A dash of length L dash, left of support A, having very high moment of inertia as shown in figure. So whenever there is a fixed support, what we have to do is we have to assume an imaginary span to the left of that fixed support whose length is L dash and moment of inertia is very high. Means we have to consider its moment of inertia is infinite. Means it does not subject to any kind of rotations, nothing. Okay. So this modification we have to do it. Once if you make this modification, now how many spans we are having? 1, 2, 3. So how many times we can apply the theorem of three moment equation? Once we have to apply A dash, A and B. These two are adjacent. The next theorem of three moment equation is AB and BC. So we will be getting two equations. So two unknown moments we are having. So by solving those two equations, you will get the unknown moments. Now let us consider first A dash, A and B. So an imaginary span has very high moment of inertia. It does not yield any M by A diagram and hence no elastic curve. So for this imaginary span, since we have assumed that there is a very high moment of inertia, it does not subjected to any slopes and deflections. Therefore, it becomes a horizontal only. There is no M by A diagram. Then what is the other span? AB. AB is subjected to uniformly distributed load. So therefore, its bend moment diagram is a parabola WL square by 8. If you calculate the area of this bend moment diagram, 2/3 BH, it is 166.67. And similarly, BC, again it is subject to uniformly distributed load. So therefore, the moment diagram is parabola. Its area is 20.8. Now, while applying theorem of three moment equation, how many times you have to apply? Only two consecutive spans first. So two consecutive spans first means A dash, A, AB once. Second time AB and BC. Let us try to apply the theorem of three moment equation first for A dash, A and B. So now if I write the theorem of three moment equation, what is the theorem of three moment equation? If you recall here the equation, this is ML into IL by LL by L, 2 times MC into LL by L plus LR by R plus MR into LR by R, which is equal to minus this. Now let us try to substitute the values. ML into LL by L. Now you see this. No. So what is ML? It is 0. ML is be there, but since M by A diagram is 0, means the left side part is 0, plus 2 times MC. What is center support now when I am flexing A dash, A and B, this becomes left hand side support, this becomes center, this becomes right. So this term is 0 and center support is MA. So 2 times MA into LL by L. What is the moment of inertia of the left side support? Infinite. So L dash by infinite plus LR by IR. LR is 10 by IR is 2I plus MB, the rate is MR. MR is the MB multiplied by LR by IR. LR is 10 by IR is 2I, which is equal to minus 6AR XR bar by IR LR. 6 into AR 166.67 into XR bar. Since it is a right side diagram, we have to consider central distance from the right side support. That is 5 by moment of inertia 2I into span is 10. So if you rewrite that equation, 220 MA, this is 0, 2 times MA by 10, 2 gets cancelled. There is a small slight mistake here. I think it is 10 MA plus 5 MB, which is equal to 6 by 20 R XR bar by R, like this. This is 10 MA plus this is 5 MB, which is equal to minus 6 into 166.67 into 5 by 10. So this equation is 5 MA plus, 10 MA plus 5 MB, which is equal to minus 500. Let us say this is equation 3.4. Now similarly, you consider the next two adjacent spans. First we have applied A dash, A and AB. Now the next adjacent AB and BC. Now while considering AB and BC, A becomes left support, B becomes center, C becomes right side support. That is very important. Left, center and right. Accordingly, we have to consider the central distance and their areas. Now if I consider AB and BC, and if you write the moment equation now, what is the left side moment? MA. What is the right side moment? Center moment? MBN, MBR, and right side moment is MC. That is equal to 0. Now you write the equation now. MA, that is ML, it is nothing but MA multiplied by LL by L. LL is 10 by I is 2I plus center moment 2 times MB multiplied by LL by L, that is 10 by 2I plus LR by IR. LR is 5 and IR is I, which is equal to minus 6AR XR bar by LR IR minus 6AL XL bar by IL LL. So if you calculate the areas and their central distances, you will get like this. And if you simplify this, you will get 5 MA plus 20 MB equal to minus 12.5. Now if you solve this equation and this equation, you will get MB equal to minus 25.6 kilonewton meter and MA equal to minus 37.5 kilonewton meters. So once after obtaining these support moments, by using simple static equilibrium equations for each span, you can find out the support reactions. Let us see that. Now we have got MA here and we have got MB is like this based on this sign. This is the span AB, it is subjected to UDL. As I explained earlier, you can find out for support reaction due to UDL, that is 2 into 10 by 2. And then you take the reaction due to unknown moments. This is the moment direction, this is the moment direction. Both are acting in the same direction. Therefore, the coupled due to reactive forces must be in the opposite direction. That is nothing but, since both moments are acting in the same direction, the reaction must be summation of these two moments by span. You will get the reactions like this. And if you find the resultant reaction, this is upwards, this is downwards, the resultant is upwards here. This is upwards, here it will be upwards, the resultant is upwards. Or directly you can write the equation like this. Take this is a simply supported beam. Take the moments about either B or A. So if I take the moments about B, Ra multiplied by 10, that is in this direction, minus 37.5 minus moment due to urea 2 into 10 into 10 by 2, that is 2 into 10 into 5. This is again plus 6.25, which is equal to 0. This is wrong, this is actually in this direction. This direction is wrong, it is in anti-clockwise direction. So that is the minus here. And since the moment due to this is clockwise, this is positive, which is equal to 0. So if you find out RA equal to 13.125 and RBL equal to 6.875. Now coming to span BC now. Similarly span BC, this is the moment, and this is the load. Now either take the moments about B or take the moments about C. If I take the moments about B, RC multiplied by span, that is in this direction, plus this moment minus moment due to UDL, which is equal to 0, you will get RC and you will get RPR. So this is the reaction on the right hand side and this is the reaction on the left hand side of B. What will be the total reaction? Total reaction is summation of this. You need not do that one. While constructing the shear for diagram also, you construct separately for this span. Immediately adjacent to this, just you consider this. Once it is, you know how to construct a shear for diagram for a simply supported beam. Just you do that. Then separately you do this. Very adjacent to that one. Let us see how it is constructed. You see this. If I take this span, the reaction is upwards. So it is upwards. Then it is UDL. The variation is linear. The variation is linear. Then left side of our reaction 6.875. So therefore 6.8. This ends. Now coming to the right side span. Reaction is upwards. Now you start from the same point upwards. Then it is UDL. Linear variation. Then reaction is upwards. That's all. This is the simple shear force diagram for the resultant beam. Now again, as I said, bend moment diagram. First you construct the bend moment diagram due to UDL. It is a simply supported beam subjected to UDL. Therefore, it is a parabola. Maximum moment is WL square by 8. So this is the bend moment diagram due to UDL, and maximum is WL square by 8. From here to here, this ordinate. Now over that, you superpose the bend moment diagram due to support moments. How it is? This is 37.5 in anti-clockwise direction. This is 6.25 clockwise direction. So it is hogging in nature. So therefore, the moment diagram will be trapezium. This is 37.5 and this is 6.25. Now you join these two. Now what is the common area? This white portion is the common area. It is removed. The remaining area is the resultant bend moment. Just you hatch it like this. This is the resultant bend moment diagram. Span AB. Same thing for span BC. See the UDL. The moment diagram due to UDL is a parabola. This is the parabola. What are the end moments? Here it is 6.25. Here it is 0. So therefore the bend moment diagram is triangle like this. What is the common area? This is the common area. You remove it, and the other area you shade it. This is the resultant bend moment diagram. So this is how we have to construct the bend moment diagram. So therefore, one can easily analyze a continuous beam using theorem of free moment equation. The most important points we have to remember while applying the theorem of free moment equation is, first we have to consider each span as a simply supported beam subjected to given loading. Then you have to construct the bend moment diagram due to given loading separately and due to end moment separately. Of course, for end moments you need not draw it, because the moment diagram due to end moments is either triangle or it may be a trapezium. After constructing the bend moment diagram due to applied loading on a simply supported beam, find out their areas, find out their centroid distances from the left support and right supports both. If you are constructing the left side bend moment diagram, you have to construct the centroid distance from the left hand side support, and if you are constructing the right side bend moment diagram, you have to construct the centroid distance from the right hand side support. The second point is the end moments you represent in clockwise direction, that is sagging, that is positive in nature. Initially you represent all the moments with positive in direction. Then depending upon the existing conditions, you may have some end moments may be 0 or it may not be 0 depending upon the type of the support which you are having. Then while applying the theorem of free moment equation, what we have to do, we have to consider two adjacent spans at a time. So first two spans, you write the theorem of free moment equation. Then second and third, we write the theorem of three moment equation, then third and fourth and fifth, like that depending upon the number of the spans. Each two consecutive spans you have to consider separately. So if you consider like that, you will get number of simultaneous equations which are depending upon the number of the unknown moments. So simply you have to solve the simultaneous equations. You will get the unknown moments. Once after obtaining the unknown moments, the simplest way to find out the support reactions are you consider each beam as a simply supported beam. Consider the loading along with the obtained end moments. First you calculate the support reaction due to applied loading. Then you calculate the support reaction due to end moment. Then you take the resultant reaction. Or else, take simply supported beam along with loading and applied moments. Write simple static equilibrium equation by applying moment equilibrium equation either to the left hand side support or to the right hand side support. Get the reactions. Like that you do it for all the spans. Then based on that only, just you draw the shear force diagram for each span separately. While drawing the bend moment diagram, the simplest way is superposition. Take each span as a simply supported beam, draw the bend moment diagram due to applied loading, and then over that you superpose the bend moment diagram due to end moments. The common area should be deleted and the uncommon area should be hatched. That hatched portion is the resultant bend moment diagram. This is the procedure we have to follow for solving the problem by using theorem of three moment equation. This is a question for you as an assignment problem. Analyze the continuation shown in figure below by using theorem of three moments and also draw the shear force and moment diagram. It is subjected to clockwise couple and this is subjected to triangular. And another question again, you have an internal hinge here. It is two concentrated loads. Here is a partly UDL. This one. So you please complete these two problems, and if you have any clarification